This research paper presents a novel approach to modeling the COVID-19 epidemic using a time-varying SIR model. The SIR model is a compartmental mathematical model that divides the population into three classes: susceptible, infected, and recovered. The classical SIR model uses constant parameters, which cannot accurately describe disease behavior over long periods. In this work, the authors introduce a SIR model with a time-varying transmission rate parameter, aiming to better capture the dynamics of the COVID-19 pandemic. The authors propose an optimization method to estimate the time-varying transmission rate parameter, based on minimizing the sum of the squares of the errors between the model and historical data. They also evaluate the model's ability to predict future disease activity using epidemic data released by the government of the State of Rio Grande do Sul in Brazil. The results show that the proposed model has a very good forecasting ability, with errors of 0.13% for 7 days ahead and 0.6% for 14 days ahead. The paper is structured as follows. After introducing the importance of understanding epidemic dynamics, the authors present the classical SIR model and its limitations. They then describe their proposed time-varying SIR model and the optimization method for estimating the transmission rate parameter. The authors also detail the evaluation of the model's predictive performance using real-world data. Finally, they discuss the limitations of the study and suggest directions for future research. The proposed time-varying SIR model and the optimization method for estimating the transmission rate parameter represent a significant contribution to the field of epidemic modeling. This work has implications for public health policymakers, as it provides a more accurate tool for predicting the spread of infectious diseases and evaluating the effectiveness of intervention strategies. Epidemics pose significant threats to public health, particularly in less developed countries where even low-risk diseases can have severe consequences. The economic development of a region directly affects the quality of healthcare and the ability to monitor and contain infectious diseases, resulting in worrying rates of mortality for treatable diseases such as malaria, typhus, and cholera. Mathematical modeling is a crucial tool for understanding and combating epidemics, as it can simulate the dynamics of infectious diseases and provide insights for control measures. The SIR model, a compartmental model, divides the population into classes with common characteristics and establishes relationships between them. It uses a set of differential equations to describe the rate of change of each compartment over time, with parameters representing rates that describe the disease spread dynamics. However, assigning a single value to these parameters may not be effective for long periods, as changes in population behavior, government measures, and the nature of the disease can alter over time. To address this limitation, this study proposes a time-varying infection rate parameter in the SIR model. The model is applied to simulate the behavior of the coronavirus in the state of Rio Grande do Sul for 770 days, with the infection rate calculated for each day using data from the Rio Grande do Sul Health Department. An optimization algorithm is applied to minimize the squared difference between the reported infected individuals and those simulated by the model. To overcome the challenge of identifying the large number of elements in the vector, a strategy is devised to gradually increase the number of entries, allowing the algorithm to converge to the desired solution. The obtained results are compared with the real behavior of the pandemic in the state of Rio Grande do Sul, and the model's validity in predicting disease activity in future periods is evaluated. This novel approach to the SIR model provides a more accurate representation of the dynamics of infectious diseases, enabling better prediction and control measures. The effectiveness of the disease behavior prediction model is evaluated by assessing its performance in forecasting scenarios 7, 14, 30, 60, and 180 days ahead. The model's accuracy is measured by calculating the percentage error between the accumulated number of infected individuals and the simulated value from the model identification. The paper is structured to provide a comprehensive understanding of the model's development and validation. Section 2 presents a simplified SIR compartmental model, which is configured as a differential equation system and simulated to demonstrate its dynamics. This model is based on the classic SIR model developed by Kermack and McKendrick, which separates the population into three groups: susceptible, S, infected, I, and removed, R. The total population N is considered constant, given by the sum S, T, plus I, T, plus R, T, equals N. The SIR model's dynamics imply that susceptible individuals can become infected when in contact with an infected individual, then recover or die and move to the removed group, following the process S right-pointing arrow I right-pointing arrow R. This simple yet efficient configuration is preferred for describing infectious diseases due to its ability to provide better predictions compared to models with multiple compartments and parameters. Section 3 of the paper describes the identification of the SIR model based on data provided by the state government, while Section 4 verifies the model's validity in predicting pandemic behavior in future scenarios. Finally, Section 5 discusses the results and draws conclusions on the model's effectiveness in predicting disease behavior. A SIR model, a mathematical framework for analyzing disease spread, is defined by a set of ordinary differential equations, ds. T dt equals beta I, T, S, T, N, D, T, dt equals beta I, T, S, T, N gamma I, T, and Dr. T, dt equals gamma I, T. These equations describe the dynamics of susceptible, infected, and removed populations, denoted by S, I, and R, respectively, with N being the total population. The infection rate, beta, is a product of the average daily encounters, E, and the probability of infection upon contact, R, which varies over time due to changes in behavior and disease characteristics. Analyzing the model reveals that the susceptible population declines proportionally to the product of susceptible and infected populations. The infected population decreases as a fraction of its size, with an average period of 1, gamma, and enters the removed group R. A key goal of mathematical modeling for epidemics is understanding disease spread, which is achieved by analyzing the model's behavior over time to identify when the spread begins to decline. Assuming a large susceptible population at the beginning, S approximately equals N, and an initial infected population I, 0, equals I0 greater than 0, we simplify the second equation to d. T, dt equals I, T, beta gamma. Solving this differential equation using the method of separation of variables yields I, T, equals I0 e, beta gamma, T equals I0 e gamma T, R01, where R0 is the infection reproduction rate, given by beta, gamma. This reveals two cases. When R0 greater than 1, the epidemic continues to grow, and when R0 less than 1, the infection tends to end over time. Understanding the SIR model's behavior, particularly the infection reproduction rate, is crucial for analyzing disease spread and predicting epidemic outcomes. In disease spread modeling, the conventional SIR model's fixed infection rate can lead to inaccuracies over extended periods. This is because the interaction between susceptible and infected classes is dynamic, influenced by individual behavioral changes in response to the disease's spread or containment measures implemented by authorities. Furthermore, the disease may mutate, affecting its contagiousness. To address these limitations, a modified SIR model with a time-varying infection rate is proposed. This model allows for defining the disease's spread on a daily, weekly, or monthly basis by modifying the parameter beta to become a function of time. The system of differential equations characterizing the model is ds. T dt equals beta T I T S T N. D, T, dt equals beta, T, I, T, S, T, N gamma I, T, Dr. T, dt equals gamma I, T. The cumulative number of infected individuals is defined as Y, T, beta, T, equals integral, 0, T, beta, tau, I, tau, S, tau, nd tau equals ns, T. Since the model lacks an analytical solution, a computational method is necessary to obtain the numerical solution of the system of differential equations. The fourth-order Runge-Kutta method is employed, solving problems of the type y, t, equals f, t, y. This method simulates the modified SIR model, enabling an understanding of the disease spread's behavior over time. By incorporating a time-varying infection rate, this modified SIR model can capture the dynamic interactions between susceptible and infected classes, as well as the effects of behavioral changes and disease mutations. This approach provides a more accurate representation of disease spread, allowing for more informed decision-making and policy development. In the SIR model simulation, a fixed period was used to align with the daily data grouping. The average infection period of 10 days was assumed, resulting in a gamma value of 0.1. The simulated SIR model is given by equations 2.7, which describe the rates of change for susceptible, infected, and removed individuals over time. This model was executed in a hypothetical case for a population of 500 over 1 month, with randomly varying daily rates. The result is shown in Figure 1, illustrating the time-varying SIR model's behavior. To identify the time-varying parameter beta, t, an optimization algorithm was applied. The method of least squares was employed, aiming to estimate the parameters that minimize the sum of a squared function f. This technique is used to fit a mathematical model based on collected data. The optimization process allowed for the estimation of beta, t, which captures the varying transmission rate over time. This approach enables researchers to better understand how the transmission rate changes in response to various factors, such as public health interventions or changes in population behavior. The objective function, j, beta, t, is defined as the sum of the squared errors between the simulated output of the model and the actual data, representing the total accumulated infected individuals over time. This function is optimized to identify the model parameters, beta, t, which are piecewise constant and vary from day to day. The optimization problem is formulated as finding the vector b, which comprises the infection rates for each day, by minimizing the objective function j, b. The vector b is defined as beta 1, beta 2, beta n1, beta n, where n is the number of days of collected data. The data used for model identification is provided by the Health Department of the State of Rio Grande do Sul, which includes case registration dates, gender, age, and other relevant information. The data spans 770 days, starting from the first registered case, and is categorized by day. The number of detected cases and cumulative infected individuals are illustrated in graphs, as shown in Figures 2 and 3, which enable the observation of the pandemic's progression, including critical periods, growth, and decline in the number of cases. The goal of the identification is to find a vector b of 770 elements, representing the infection rate corresponding to each day. For instance, the value at position 20 of the vector b represents the infection rate on the 20th day. The optimization algorithm, F-MinCon in MATLAB, is used to find the optimal values of b that best fit the actual data. This algorithm is employed to identify the model parameters that minimize the objective function, thereby providing an accurate representation of the pandemic's progression. The model's performance is evaluated by analyzing the daily cases and accumulated number of infected individuals in the Rio Grande do Sul, RS, state. Figures 2 and 3 illustrate the actual number of daily cases and accumulated infected cases, respectively, with the z-axis representing days and the y-axis representing the number of infected individuals in thousands and millions, respectively. The infection rate, beta, is determined by aligning the simulated graph with the real behavior observed in Figure 3 using the cumulative infected data from the previous subsection and an optimization method. The model, as described in Equation 2.2, is simulated using the Runge-Kutta method with initial conditions established for each state variable. The initial values are set as s, 0, equals p1, I, 0, equals 1, and r, 0, equals 0, where p is the approximate total population of Rio Grande do Sul, estimated at 11.3 million, as shown in Equation 3.5. To optimize the parameter vector b, initial values are assigned to its components. This optimization process enables the estimation of the infection rate, beta, which is crucial in understanding the spread of the pandemic in the RS state. To address the challenge of inaccurate estimates in non-convex optimization problems, an iterative algorithm was developed to approximate real-world behavior based on available data. This algorithm initializes with a single element vector bh, assigning an initial value of beta equals 1, to approximate the model's behavior. The optimization algorithm is executed, resulting in a large error. In subsequent iterations, the number of parameters is doubled, and the previously optimized values are assigned. This process is repeated, with the number of elements in vector b increasing exponentially until precision improves. As shown in Table 1, This iterative strategy yields a final vector with 1024 elements. The last 253 elements, 771st to 1024th positions, are discarded, and one rate is optimized for each day, resulting in the identified vector B. Figure 4 compares the graphs, demonstrating the model's achieved accuracy. By simulating the model based on the identified rates, the system's behavior is observed in Figure 5. This data-driven approach enables the determination of infection rates for each day of the pandemic, allowing for precise observation of the behavior and evolution of infections. However, this technique is limited to understanding past behavior, raising questions about its potential to forecast future behavior. This study assesses the model's effectiveness in predicting disease activity in the days following the known data, exploring its potential for forecasting future behavior. The predictive accuracy of the SIR model is assessed by evaluating its ability to identify infection rates and forecast the pandemic's progression over different time intervals. Assuming the pandemic has reached its 100th day, the infection rate for each 100-day period is estimated, with the assumption that this rate continues from the 100th day onwards. A comparison of real-world behavior with simulated data, as shown in Figure 4, reveals a close match between the two, suggesting that the SIR model can accurately predict the spread of the pandemic when provided with accurate infection rates. Figure 5 illustrates the simulation results using the identified infection rates, demonstrating the dynamic changes in susceptible, infected, and removed populations over time, as well as accumulated cases. The simulation highlights the model's ability to forecast the pandemic's progression accurately, particularly in terms of the peak infection rate and its timing. The findings indicate that the SIR model can be a valuable tool for predicting the future course of the pandemic, given accurate estimates of infection rates, informing public health policy and resource allocation decisions. However, this analysis is limited by the assumption of a constant infection rate post-100 days, which may not reflect real-world variability. Future work could involve incorporating more dynamic infection rates or other factors that might influence the pandemic's spread. Evaluating the predictive accuracy of the proposed model is crucial for understanding its ability to forecast the cumulative behavior of the pandemic. To achieve this, the authors assess the model's performance in predicting the cumulative number of infected individuals over various time intervals, including 7, 14, 30, 60, and 180 days. The percentage error between the predicted and actual cumulative number of infected individuals is calculated using the equation E_t, t equals frac y, t plus t hat y, t plus t y, t plus t, where t represents the respective time intervals. This process is repeated starting from the 101st day and continues successively. For each time interval, the average percentage error and its standard deviation are computed. The results for the 7-day prediction interval show that the percentage errors are distributed in a histogram that closely resembles a Gaussian curve. The mean percentage error is 0.13%, with a standard deviation of 1.08%. Notably, most cases fall within this range, indicating the model's reliable predictive capabilities in the short term. By evaluating the model's performance over various time intervals, the authors provide a comprehensive understanding of its strengths and limitations in forecasting the pandemic's cumulative behavior. This analysis is essential for informing public health strategies and resource allocation. The predictive accuracy of the model in forecasting pandemic behavior is evaluated for 1, 2, and 4-week ahead predictions. 1 week ahead, the model demonstrates good accuracy, with a mean percentage error of 0.2% and a standard deviation of 1.2%, indicating that most predictions fall within one standard deviation of the mean. For 2-week ahead predictions, the model's performance decreases slightly, with a mean percentage error of 0.6% and a standard deviation of 3.13%. Although the error distribution still resembles a Gaussian curve, a higher number of simulations exhibit errors exceeding one standard deviation from the mean, suggesting reduced accuracy. In contrast, attempting to simulate pandemic activity 1 month ahead reveals a significant decline in accuracy, with an average percentage error of 3.95% and a standard deviation of 12.48%. Notably, the error distribution no longer follows a Gaussian curve, in many cases deviate significantly from the mean, indicating a lack of fidelity to the actual pandemic behavior at this extended time horizon. Here, the predictive capability of the model was further assessed by forecasting the pandemic's behavior 180 days into the future. The results showed a significantly high percentage error in almost all cases, as illustrated in Figure 10, which displays the distribution of cases alongside the corresponding Gaussian curve. The average percentage error was 123%, with a standard deviation of 242%, confirming the impracticality of using the model for long-term predictions. The paper concludes by emphasizing the importance of understanding epidemic dynamics to inform prevention and combat measures. It proposes a simplified compartmental SIR model to describe the coronavirus pandemic, but notes that the conventional system of differential equations relies on constants with fixed values to represent the infection rate, which can lead to inaccuracies in simulating long periods of time. To address this, a time-varying infection rate was adopted to reflect the daily activity of the disease, with a value identified for each day using data on the population infected by COVID-19 over a period of 770 days in the state of Rio Grande do Sul. An optimization algorithm based on the method of least squares was executed to determine the infection rate. This approach highlights the need for more nuanced modeling strategies that account for the dynamic nature of epidemic spread. The results underscore the limitations of the proposed model in predicting the pandemic's behavior over extended periods, emphasizing the requirement for continued refinement and improvement of mathematical models to better inform public health policy. The authors developed an iterative algorithm to identify the parameters of the model, doubling the number of elements in the vector to be identified after each iteration, due to the non-convex nature of the optimization problem. This approach enabled adjusting the model to the data, resulting in high accuracy in representing the accumulated number of infected individuals, as observed in the graphs comparing the simulation with real-world data. The identified model demonstrates high accuracy in capturing the evolution of the disease, indicating that it is complex enough to represent the pandemic's development, and that models with more compartments are not necessary. To evaluate the model's validity in predicting the disease's activity in future scenarios, simulations were conducted 7, 14, 30, 60, and 180 days into the future. The results show that the model can reasonably accurately describe pandemic scenarios 1 or 2 weeks into the future, with a percentage error of less than 0.13% when simulating 7 days ahead, and less than 0.6% for 14 days. However, for time intervals greater than 14 days, the model's predictive accuracy deteriorates significantly, with large generated percentage errors. The main source of error is the choice of a constant value for all days ahead, as the infection rate varies significantly from one day to another. A key area for future research is exploring alternative functions for the upcoming days to improve the model's predictive capabilities. The authors highlight the need for more sophisticated approaches to capture the dynamic nature of the infection rate, which is crucial for accurate forecasting and informed decision-making. Please provide the content that needs to be refined for the explainer video. The instructions were clear, but there was no content provided. Please paste the original transcript, and I will transform it into a direct, concise form suitable for voiceover narration, maintaining the technical accuracy, depth, and tone required for expert researchers and stakeholders.